So what we're going to do is we're going to take a device called a capacitor, and we're going to hook it up in parallel with the output. By the way, this is all in what chapter? Are we in chapter 6? Textbook. I'm gonna have to find my textbook, folks. I don't know what to do. So we're moving from here over to where? Yeah, we're moving from here over to here. So what's the function of the rectifier? What's the function of the transformer? Okay, that's good. But it is there to establish the voltage needed by the load. So you don't just choose it to step up or step down. You choose a transformer to get the voltage required by the load. And it might step it up or it might step it down. So that robot over there runs off DC. But to get the DC that's required to make the robot run, it requires 440 volts worth of AC coming in. That's what it requires. And we don't have 440 volts AC here, so they had to choose a transformer that took the high voltage single phase or three phase we had here and do what? Step it up. That makes sense? The same thing true with the big FANUC over there. All these robots are 240 robots. So the Motorman, the FANUC, and the little KUKA are all 240 robots. We plug them into a wall outlet over there, which is 120 volt. It's 120 volt, 20 amp circuits. So what has to be over there on those robots? Transformer. And how did we choose a transformer? Well, we knew the robot needed 240. We knew we had 120 volts here, so we needed to step it up, and that's the way and then we had to choose one that had the right power rating, right? So we start off with a transformer. The purpose of the transformer is to set the to be able to run the load. So we're going to choose it to give us the output voltage we eventually want to get to, and also the power that the load needs, right? Now, what's the function of the rectifier? What does it do? And it takes AC and converts it into pulsating DC. And then what are the filters going to do? It's going to take DC, it's going to take pulsating DC and convert it into unregulated DC. And what do we mean by unregulated? It varies with load and input. And then eventually we're going to add a watt out there. We're going to add a regulator. So if I put a little battery out there, and and let's say it's a little positive battery, so I put it in there like this, and this thing charges real fast and discharges real fast, and I put that little old battery in right there, and then of course what would happen is that in here it would do what? It would charge it. Does that make sense? And as soon as this started dropping down, then as soon as it dropped down below the voltage that the battery charged up to, then what would the battery do? It would run the load. But as soon as you put power, as soon as you require something, look at your phone. So you charge your phone up and you take it off that charger, and it's almost no time, it's already at 99%. Then it keeps doing what? It constantly does what? Discharges until you do what? Charge it up. So if you were to look at the output of your battery, it's doing this. And how far does it drop? Well, if you don't charge it up, it's going to drop down to nothing, right? Your phone will eventually turn itself off. Well, what we're doing right here, if this is half wave, what I'm doing right here is I'm going to come up here and hit it with this, and what's that going to do with the battery? It'll charge it back up. This charges the battery up to the maximum voltage, let's say 10 volts. Well, as soon as this drops down below 10 volts, what's going to happen? Well, that battery is going to take over the load because it has the most voltage, right? You understand? And what's it going to do again? It's going to discharge down until what? Until the next alternation. So that's what the capacitor is doing. The capacitor is acting just like a little rechargeable battery. That's all it's doing in life. And it discharges extremely fast. How fast does it discharge? How fast is your phone discharge? So if I leave it in my dang pocket all day long, you know, I can run that sucker. I can all night. I never answer a call. Nobody ever calls me. I get it. I come home at night. I look on it. It's probably still 87, 80%. Right? I play games on it all day long. I have my display on. I turn my lights on. Then that sucker is going to discharge extremely fast. Right? So what determines that? Well, what determines that discharge rate is the amount of current that we're going to have to get out of that battery. The more current we get out of it, the faster it's going to discharge. So here, what's going to determine how fast it discharges is that load we put out there. The bigger the demand, the load requires of that capacitor, the faster it's going to discharge. So the current of the load depends on that. Now, capacitors are, of course, batteries are rated in volts, right? They're rated in volts and amps. Capacitors are rated in their ability to store a charge. And we call this capacitance. And it's referred to as, it's measured in units called farads. So the bigger the farads, the more of a charge it'll have. And it stores what we call, y'all know what a coulomb is? Did y'all learn, what's a coulomb? It's basically, but it's 1 amp of storage. It's 1 amp of storage. So a coulomb is equal to 6.25 times 10 to the 18th electrons that are not in motion. That's exactly what it means. So 1 amp is 1 coulomb of electrons, but now they're what? They're moving, right? So coulombs is the rate is what. So capacitors are rated in farads, and it's a formula that you would calculate the number of coulombs it can store. But what we need to know is the more farads it has, the more coulombs it's going to store, the more amps it's going to store, right? You understand that? And the longer it's going to be able to run my load. But it's just like going out and buying bigger batteries. So I go out and buy a AA battery, and I go up and buy a D battery. What changes? They're both rated at 1.5 volts. What changes between a AA battery? What? The amp hours are the amps, right? And what else changes? Well, you're right, the size, but so the same thing's true in capacitors. So the more storage capacity a capacitor has, the bigger it's going to be, and the more it's going to what? It's going to cost. So sizing your capacitor is very important. Either that, or you're not going to put a capacitor in there that's big enough to run the load, or you're going to put one in there that's too big, and you've just wasted a bunch of money. So we can calculate the discharge rate of a capacitor in time. Anybody had AC? Anybody know how to calculate time for a capacitor? It's equal to R times C. Very simple formula. And this is what we use here. In actuality, it's how long it takes to discharge it to 63%, by 63%. But here we're never going to let it get close to that. So this is the guy we're going to use to calculate this formula right here. This is the guy. Because we're not going to ever let it discharge all the way down to 60. Because before it discharges, we're going to do what? We're going to charge it up. Everybody understand it? So I got to get so what would see so if I know this and I'm trying to calculate this voltage right here. So I'm trying to calculate how much voltage it would discharge down before it does this. Then I got to get V in the formula. So time is equal to R times C. How can I get V in that formula? Nobody knows. I'm going to use something called Ohm's Law. Ohm's Law says something is equal to R. If something is equal to R, if they are equal, what does that mean? That means I can replace them in formulas. So I'm going to put T here. What does Ohm's Law say R is equal to? Huh? Okay, so I can say V over I times C. That's exactly the same thing, right? Y'all understand? That's it. And people don't understand that. If I've got something that's equal, that Ohm's Law says R is equal to V over I, that means anytime I see R in a formula, I can replace it with V over I. And that's where all your wattage formulas comes from, right? You understand? What's the main wattage formula? Wattage is equal to V times I. Well, where in the heck did V squared over R come from? Where in the heck did I squared over R come from? Well, what they did, they said, okay, what's V? What does Ohm's Law say V is equal to? Okay, so if V is equal to I times R, that means I can say V is equal to I times R times I, and that's exactly the same thing. So there's I squared R right there, right? You understand? So all they did to get those other three power formulas is they took that formula right there, and then they substituted for V what Ohm's Law says V is equal to, and then what Ohm's Law says what? I is equal. What's I equal to? So here's my V. It's equal to V over R. V over R. So I got 2 up there. So power would be equal to what? V squared over R. That's your Ohm's Law formulas right there. So you got to understand this is what the power of Ohm's Law is that from now on, when I'm trying to figure out this stuff, right, you understand, if I've got R, I could always replace it with what? V over I. So now I got V. So this is the size of that voltage right there. And we're going to call it V ripple peak to peak. Now I got to solve for V ripple peak to peak. So how would we solve for that? Y'all got y'all's equation sheet. You can look. We got 2 formulas. What's that? Well, we're not there yet. The other one. Yeah, I of the load. That's got a head is over what? See? That can't be it. There's got to be a T in there somewhere. Where's it at? So this right here would be the size of my capacitor in what? Farads. This right here would be the current in the load. That would be the time that it's going to have to run the load. So how long would it have to run it here? Well, it's going to have to run it for what? It'd have to run it for 16 milliseconds, 16.7 milliseconds. But the other formula we like is T. So this is the period, right? You understand that? So it's equal to, the time is equal to 1 over F. So what I can do is, if time is equal to 1 over F, then what can I do? I can use 1 over F. So this is the formula I like to use. V ripple peak to peak is equal to IL over C times A. So now if I'm saying if I got a half-wave power supply, I would use my input frequency. If it's a full-wave power supply, I would use twice the input frequency. Does that make sense? So that's where that formula came from. So if I know that, and I can transpose, think about this. I can transpose this formula right here for a ripple voltage. I can solve for C, right? You understand? So that's why we would solve for what C is required. So what I'm going to do is I'm going to take that capacitor and I'm going to put it placed in parallel with the load. For positive power supplies, so this would be the way we'd hook it up. That's all there is to it. And by the way, the thing that determines the amount of capacitance, so a capacitor is nothing but, we make capacitors all the time. You're a good capacitor. We charge ourselves up all the time, right? You understand? Well, why do we need to have a capacitor? They know. Very easy to make. We watched Mythbusters make a capacitor out of some PVC tube. Which is pretty. They were trying to generate enough voltage up to what they really need. They took a metal rod, run it down the center, and then they sprayed the outside pipe with metal paint. So basically, all we need is two conductors that are close to each other. We call them plates. So we'll tear one apart. Let y'all show it. So what we do is we have two conductors. We put them together, and then we make connections to them, and that makes a capacitor. That's all it is. And what happens is that when we cut, so we charge these things electrostatically, kind of like you when you build up a charge. So what determines the amount of capacitance is the size of the plates, the distance between the plates, and then the material used as an insulator. So you got to have an insulator. Now, what determines the capacitance is how big the plates are, how close we can get those plates together. So the closer you can get them together, the more they interact with each other and the size of the capacitor goes up. And of course, what you use for that material, we call it a dielectric constant. That's related to air. So, now the problem is that we start getting those plates real close together. Our insulator starts getting getting smaller and smaller. Then we're going to punch through the insulator. So one of the big things a capacitor is related at is called working voltage. And that's the maximum voltage you can charge that capacitor up to. If you charge it up too much, you'll punch through the insulator, and the capacitor is going to start conducting through so there's no current flow through a capacitor. That's the big thing, the difference between a battery. A battery, the current flows through the battery, right? You understand? So all the battery does is push the current in the loop. A capacitor, when we charge it up, there's no current flow through it. Capacitors do not get hot because there's no current flow through them. So to get work, you got to push current flow through them. Well, the problem is if you punch through that insulator, now you have current flow. If you have current flow through the capacitor, then you got Watt's law coming in. These things are all sealed up, and what happens when we start heating up stuff? It expands. These suckers will blow up if you exceed the working voltage. So when we buy capacitors, we're concerned with two things. We're concerned with the amount of capacitance I need and the amount of working voltage. Well, if I start making the plates, if I start spreading the plates out, I can make them bigger and get the same capacitance. Does that make sense? But we're looking at hundreds of microfarads. So what they do is they polarize the plate. So they develop one metal that really likes to store a positive charge, and then the other metal likes to store a negative charge. And now these are polarized capacitors, which means, by George, if you put these suckers in the circuit backwards, they will blow up if you don't protect them. And we're going to be putting them almost directly across the transformer. So there's no resistor protecting that capacitor. So if you put that sucker in there backwards, it's going to start acting like a resistor because you change the polarities of the plate, right? You understand? Current flow is going to go through the dielectric, now we got I flowing through R, and what's it going to do? It's going to heat up and blow up. So we're going to be dealing, so your filter capacitors are going to be polarized. And what that does is it allows us to use smaller size plates to get the same farads and still separate them out enough, right? You understand, to get the working voltage up. So they polarize the plates. So by George, when you hook these, and so when you look at a polarized capacitor, and I'm going to show y'all those, these polarized capacitors, one of the leads is going to be labeled with a polarity. They're either going to label it with plus or they're going to label it minus. And it's only got 2 leads. So if they label one of them minus, what does that mean? The other one's plus. If they label one of them plus, that means the other one what? It's minus. And by George, and I'll show y'all the video, by the way. We've got a guy, Jamico, actually deliberately blew, we call these electrolytic capacitors, by the way. These are polarized capacitors. And these are the big guys. These are the 10,000 microfarad. These are the big guys. We got a 10,000 microfarad in a power supply over, and we need to, if it hadn't been thrown away. And if you hook it up backwards, what's going to happen? Yeah, it'll pop on. It won't, usually don't send out shrapnel, but it sends out a lot of smoke, and it'll pop. We used to, might pop one on purpose. So what determines that is the working voltage. So what you're really concerned with is make sure you choose a capacitor that exceeds the working voltage, probably by about 50% of working voltage of your circuit. So here we're dealing with 12. So what should the working voltage of our capacitor be? So we're dealing with a 12.6 volt transformer. When we go to full wave, they're going to see peak to peak. And this is not RMS. This is peak, folks. Especially when we charge them up, because it stays up the whole time, right? You understand? So we put that capacitor in there. We're going to have to block peak to peak, because when it charges up, the other side is negative, right? You understand that? So what's the peak to peak voltage? 12.6 volts peak to peak. What's that? Okay, so we need to probably use one that's rated at about 50 volts. So look at that when you get your capacitor, if there's one in your kit that y'all been using. We should inventory the kit too, but make sure y'all have everything there. We want to use one that's rated about 50 volts, right? I think they're using look at y'all's lab and see, they're using a 10 microfarad or 100 microfarad. I think it's 100. Yeah. So we need 100 microfarad, 50 volts. Or you can calculate your ripple voltage by what? So my ripple voltage would be equal to what? V ripple peak to peak is going to be equal to what? I of the load divided by C, so R times the frequency. Now, how are you going to guesstimate I of the load? Anybody remember last class? It's a rough guesstimate. Well, the only difference between so that's V peak out right there. So that's V peak out. Now, my DC average is going to be right down the center. My DC average is going to be right down here. If that's supposed to be the center there. I understand that. So when we calculate I of the load, we'll use VP. So I of the load is going to be equal to approximately VP over R. Now that's not true. It's actually going to be a little less, but it's going to be close enough for solid state, right? You understand? And then I can take that and plug it into this formula right here. What are we going to use for C? 100 micro. What are we going to use F for F? What are we going to use? 60 for half wave, 120 for full wave. Right? And that way that gives us a good idea of what our ripple voltage is going to be. V peak over pi is gone. 2V peak over pi is gone. That only works when we work with an alternation. Here we're not working with an alternation anymore. We don't have pulsating DC. We have unregulated DC. The only difference between our average voltage, which will be right down the very center of that line, the only thing that's the only thing difference between V peak and now in my output voltage. So what does it say my DC output's equal to? It's equal to V peak out minus V ripple peak to peak divided by 2. You understand why? Because that formula calculates this. My DC is averaged in the center of that, right? You understand? Which is exactly 1/2 of V ripple peak to peak. So man, we're going to get almost V peak out of this. I mean, it's almost. And the smaller the load, the closer. You can take that load off and this sucker will be VP. Because there's no I anymore, right? You understand that? If there's no I of the load, then what would my output be equal to? My V ripple peak to peak would be 0, right? Half of 0 is still 0. So yeah, if y'all pop that load out of there, you're going to get pure DC, beautiful DC. You can turn that scope down as far as you can and you're still going to see real pretty DC. As soon as you hook a load up to that thing, you're going to start seeing what? You're going to see that slant. And what determines the size of the slant? The load, how much current the load needs, right? So the more current you require, so if you put a, I don't know if they, I think they tell you that in the lab, you put a resistor in parallel, what should you expect V ripple peak to peak to do? Should go up. Your average DC now is going to shift down with that, right? You understand? So you'll see, you should be able to see that thing vary with the load. So I think one of the things they're going to have you do with the lab is going to have you stick another resistor in parallel, and now you know what to anticipate. In fact, you can calculate it if you want to. I don't think they require you to do that. But what should happen if we load this thing down? We should see V ripple peak to peak go up, and if V ripple peak to peak goes up, what's going to happen to my average output? It's going to go what down? If my load goes up, if my load goes down, V ripple peak to peak is going to go down. My average output is going to go up, and that's going to be that's why it's unregulated. If you go home and you do this, and you got 115 volts at home, it's going to be lower voltage. We got 120 volts here. It's going to be higher, right? You understand? So this output is going to vary not only with the output load, it's going to vary with the input too. And that's what unregulated means. All right, guys. Go take a break. Go to lab. So let me move the table back over here where the air hoses are for the robots.